Dear participants, good morning. Welcome to first special session of symposium. Dear Berna Yanıkoğlu will give his speech. Dear Berna Yanıkoğlu is professor at Computer Science and Director of Center of Excellence in Data Analytics at Sabancı University, Istanbul, Turkey. She received a double major in Computer Science and Mathematics from Boğaziçi University, Turkey in 1988, and her PhD degree in Computer Science from Dartmouth College, USA in 1993. Professor Yanıkoğlu worked at Rockefeller University, Xerox Imaging Systems, and IBM Almaden Research Center. Before joining Sabancı University in 2000, her research interests lie in the intersection of computer vision and machine learning areas, currently focusing on unsupervised learning of face attributes, handwriting recognition for autonomous text, medical image understanding, and text summarization. She is an editor for Turkish Journal of Electrical Engineering and Computer Science. Dear Berna Yanıkoğlu, here you are. If you are ready, you can start your speaking.
Okay, thank you. So I'm Berna Yanıkoğlu. Thanks for the introduction. Okay, so today I'm gonna have a half an hour talk on computer vision, where it's going with deep learning. So you all know object classification in computer vision refers to identifying the object in a given photograph. Then more complex tasks go from object detection to object localization to semantic segmentation. So where detection can locate multiple objects of different types in a given image, maybe in terms of bounding box. Semantic segmentation talks about pixel-wise, addresses pixel-wise labeling. Can be used in remote sensing. And another task is image captioning, that is with words and phrases describe the image content. So the progress has been really, really amazing in the last just few years. One particular use of semantic segmentation or object detection is in autonomous cars. The history has started from roughly the deep learning history from 2012, where there was a huge, significant jump, reduction in error in the ImageNet computation. Later, it was followed by some significant advances. One is in 2014, we got the generative adversarial networks idea, where two models are trained in a minimax fashion, where one tries to generate a fake image and the other is trying to detect whether this is a fake image or a real image. So when they are trained together, they actually both can perform, improve their performance so that the discriminator can really learn how to separate real from fake, and in doing so, it actually helps train the generator produce more and more realistic looking images. This started in around 2018 with low resolution images, so they weren't like maybe that impressive, but come 2020, the images generated by such models are so impressive that regular people started to follow AI technologies and be impressed by it. So now the images have higher diversity, higher quality, and we can even control the image attributes. We can say generate an Asian female with eyeglasses, short hair, and so on and so forth. These also sort of later 2018, we did the style transfer with generative models where you can take an image, You can show the night view, day view. You can take a black and white image. You can color it. You can change season. You can go from sketch to realistic images and so on. Then later on, we got language models, which started in 2018, and the most recent model came up very recently, a couple of weeks ago. So there's DALL-E from OpenAI that generates, for instance, when you say avocado chair, it generates these images, which are amazing, we thought at the time. Now we are even more amazed. Then came GPT-3, GPT variants starting from 2018, again from OpenAI. This one completes a given text prompt. It can complete the rest of it. Okay? So that's basically what a language model is, predicting the next word. These do have still some challenges. They're based on transformer models, so the input size is limited. They are pre-trained models, so if you actually tell them something, it's not continuously learning. And finally, they are not really explainable models, as is the case like most AI systems. And then when we were impressed by this came Stable Diffusion from Stability AI, just August of this year. And this was a game changer. It's even more successful than DALL-E or other models. So you see some, given a text prompt here, like a Boston Terrier Jedi holding a dark green lightsaber, etc., it creates these images all by itself. Or here's some other images where the prompt may be something like a teddy bear astronaut on the surface of the moon, etc. Very, very impressive. It also brings new issues. Now, I have recently heard that an artist is complaining that his style is generated by Stable Diffusion models that are publicly available. And so it just basically copies that artist's work through his available work. So it just copies, learns, generates images in that style. So interesting sort of areas are coming. Interesting problems, interesting issues. You all know about deep learning. So we had shallow networks, especially with the convolutional architectures. We go now deeper and deeper with our neural networks, and the parameter size is increasing, but so does the power also. The concept is transfer learning, where you can take a pre-trained network that has sort of learned what are the useful features, and you apply it to a different problem using a much smaller data set. We have, for instance, taken a general object classification network, and we have applied it to COVID detection on CT scans. Data augmentation and, in general, data availability is a big issue in these, where we take an image and we can rotate it and translate it, reflect it, and so on, in order to generate more images of the same. At this point, I'm going to start with some of our projects. So recently, my PhD student, Sarah Tito Ali Ahmed, has graduated. She worked on face attribute classification. This was a TÜBİTAK supported project. In here, the task is given a photograph of such as a face or an item, clothing item, try to extract attributes of that image. Try to say whether this person is old, bald, man or woman, etc. So these are attributes. They're extremely useful in zero-shot learning and so on. There's the issue of binary classification. Is it bold or not? Is it smiling or not? Or actually, sometimes that's not enough. So we go to relative attributes. In other words, we try to compare images. Like this is more sporty than that. These are equal in sportiness, and so on. We have several papers on the topic. So I'll go through them a little bit. There are some key ideas that I want to mention. In one of them, we said, ensemble methods work, but deep learning ensemble is very costly. I don't want to train 5 deep networks. Each take at least a few days or a week or so. So what we did is we call it within network ensemble. And what we did is we have one network, and from 5 different layers, we spawned, created new output layers. And in other words, we want this network to learn the task, this network to learn the task, this network to learn the task, and so on. And this idea actually worked. And we got some state-of-art results in 2019. Another work, again with Sarah, was about relative attributes. How do you compare which one is smiling more in these 2 images, for instance? So you can use what is called the Siamese network. You use the same network, you feed the 2 inputs, but the 2 networks are trained with shared weights, and then at the end, typically you have a shallow network that does the comparison after the Siamese network sort of computes the useful encoding or representations of these 2 images. We obtained very good results with this approach as listed here. So in other words, we can actually quite successfully compare the attributes of 2 images. But right now, the approach for this is per attribute, so per gender, per smile, and so on. We train a new model. Actually, it learns quite well. So this is the open mouth attribute. You see that from closed mouth, the system can assign a score of -1, sorry about this, and then to almost +1 in this image. And going from closed, open, not open shoe to open shoe. Another work that we are doing is with my other PhD student, Mehmetcan Yavuz, who is about to graduate soon. He is looking into self-supervised learning field. So the idea here is we have a ton of data in forms of images and videos on the internet. But they are not labeled. That is, we don't know whether this is a CT scan with COVID, but we have lots of CT scans. We don't know whether this is an image of a bird of this type, but we have lots of images like this by people sharing and so on. So how do you make use of these abundant unlabeled data? So comes self-supervised or semi-supervised approaches. So semi-supervised approaches say I have a little bit of data and a lot of unlabeled data. So how do I go about it? Self-supervised is a little even more interesting. So for instance, the idea was suggested a couple of years ago. They train a network, given an input image, rotated in an arbitrary but fixed set of angles. The model just tries to understand what is the rotation angle. So if it takes this, randomly chooses to do a 90-degree rotation, here's the rotated image, the network tries to learn and predict that this is a 90-degree rotation. This is a weird task, but it's called a pretext task. And it actually, in order to do this, the network has to learn what is a bird and the features or the encoding of these types of images. Another thing that Mehmet is in particular working on is called contrastive learning. where this is a self-supervised approach. You say, if you take an image and if you take two augmentations, those augmentations should give you similar representations, as opposed to some other images in your mini batch where the representations should be unsimilar. So that's the main idea, and this was published in the ICPR conference. Another main approach that he's using is applying all of these in a variational fashion, as in variational autoencoders, to represent more robust features. Some other tasks that we are, some other projects that I have been working on is handwriting recognition. So all older generations will know it as OCR. It's also called as ICR, intelligent character recognition, and so on and so forth. So over the years, I have had some collaborators and students, Alişer Kolmatov, Esma Fatima Bilgin Taşdemir, Fırat Kızılırmak, Kemal Nazar Hoca, who's now in Qatar CMU, and so on. And now we are actually even collaborating on Ottoman document recognition with Mehmet Kuru from Sabancı University History Department and Esma Fatima Bilgin Taşdemir from Medeniyet University. So this work is also supported by some TÜBİTAK grants. The task here is given some handwritten image, the handwritten image of a text. This shows some of the variations converted into machine readable format like ASCII characters and so on. We have worked on it for English, Turkish, and now the Ottoman script. And the task is, what is the words given the image? So we can sort of use this notation. And it involves two things. One is the optical model. What does this shape look like? And one is the language model. That is, what words is likely to follow within this context. And this part in particular is very difficult for Turkish, that is for Turkish and Ottoman script Turkish, Turkish written in Ottoman script. So because we have so many words in our lexicon, okay? So this is in particular a particular challenge in agglutinative languages, because then they have very large lexicon sizes. We have used, so Fırat has taken this input, used a convolutional layer, followed by an LSTM recurrent network, and followed by a CTC decoding, and followed by word beam search decoding to work on historical and other English documents and obtain very good results. And now we took this work and developed it further to take a page of Ottoman document. So Ottoman document means it's a Turkish word written in mostly Arabic and also some Farsi characters. So only the script type is different, but this is, so it says here salladıkları, mendilleri, hararetli, and so on, going from right to left. This is, our project is called Akis, to sort of, it's a wordplay for how it's reflected this way and how it's reflected from this script to our script. This is how successful it works for this relatively simple document type. Just very few errors. One word missed here, one period missed here, one comma, I think, added there. This is a really hard problem, actually, that has been addressed for many years without much success, because in Arabic, you have some characters here, but they could correspond to multiple characters in Turkish, and vice versa. There's a lot of variations in writing, and vowels are often skipped in Ottoman text. So when you see this, it could be avlu, evli, ölü, ulu. It could be any of these four words. So how do you decode? Well, depending on the previous words and so on, hopefully. We have above 90% word recognition accuracy. This project is, or we expect with the simpler documents. So the goal is to go to much more challenging document formats, such as those that are not fully separated like this, that could be dirty, that could be handwritten, and so on. But the small tests right now is very promising. Another work that is in collaboration with Professor Erhan Abdullah, who's now at Sabancı University, is on plant identification. And I'm also working on plant disease classification from images. The task here is from one competition such as this, given unconstrained images of plants. There are 10,000 classes that are very similar. Just imagine the difficulty of identifying any of these. We obtained actually close to 75% accuracy in 2008, matched one human expert and on very little computational hardware. Another problem that people work on in roughly these areas is smart agriculture, where with drones or with just farmer using a smartphone, can they take a picture and quickly identify the diseases of plants that are affecting the plants? So it's not the plant identification, but plant disease or deficiency or pest identification. I have also recently started looking into medical image understanding. One work was with Sarah and Erhan Abdullah about skin mole classification, and another work was supported by TÜBİTAK about COVID-19 infection, detecting COVID-19 infection in chest tomographies. In skin moles, you have an image of a skin mole taken by a smartphone, hopefully, and then so you want to classify it as one of the skin cancer or healthy type. And this will be very useful because people are often late and this is an aggressive type of cancer and so on. But the challenge here was that you have data from 8 skin cancer types, but there's also so many other types that the competition asked us to say, this is none of these 8, it's a different category. So this becomes an open set problem and it's really difficult to solve. So we have about 60% accuracy among these, but it was sort of one of the top contenders at the time. Another work that we did during the pandemic was about COVID-19 infection detection. This was in collaboration with the Cerrahpaşa Hospital Radiology Department. What we did is, given a CT scan illustration like this, these sort of areas indicate that there could be COVID-19 infection. So there's some symptoms shown in the lungs. How do you detect this? Again, another image understanding problem by sort of looking at these parts of lung areas and trying to see these smoke-like patterns or broken glass-like patterns. We were able to do a very successful system and installed it actually at Cerrahpaşa. So what we did is we took the image sequence, we passed it through a neural network, then we can sort of average them, or we actually use the recurrent network to learn the information in the sequence. And in another approach, we treated this CT scan as a 3D input directly. Our results are very good. They're above 90, even in a data set which we had never seen before, surpassing many of the systems in the literature, even though we haven't trained for this system. So this was on the news. This is Mehmet and Sarah and Umut and the Cerrahpaşa team who achieved this, and this was used during the pandemic to say that to mark those CT images that look like infected so as to speed up the evaluation, treatment, and so on, and to lower the virus infection pattern. We have some new work with Erden Özer Hoca from Ege 9 Eylül University, and who is now in Sidra Medicine, Qatar, about brain tumor classification. That is also interesting. So during the operation, doctors need a quick and accurate diagnosis of what kind of tumor is this tumor that they know and are operating. So we have taken a similar sort of deep learning approach where these images are huge, so we look at them in parts and we try to combine the result. This is also to appear in a future publication. So I'm finishing up. This is my last slide. Some really significant progress has happened in AI in the last just 5 to 10 years. Computers now surpass humans at many perception tasks, computer vision being one. There's a rapid progress in large language models and joint image to language models. There's more work on self-supervised learning is also showing great progress. What are the shortcomings? So some of the shortcomings are, this is very resource-hungry research. So you need lots of data, you need lots of computational power in order to sort of match what these big companies are doing. And when those big companies are doing their work, they're consuming a lot of energy, for instance. Then a second sort of group of problems is about explainability and bias and fairness of AI systems. So they may say this patient has cancer, but what have they seen to say that? Normally one doctor would show some patch to another doctor to explain their reasoning, but this is sort of lacking still in AI system. Another one is bias issue. That is, we are so far training all of these AI systems with whatever we have in our collective human culture and produce documents and produce work and so on. So what they are doing is they're learning from there. Whatever bias we have is reflected exactly in the AI systems. Yet a third group is about privacy concerns. There's also related security concerns. So there's a research area called adversarial machine learning. A new concept actually now is what I mentioned before. So when someone draws like you or writes like you or, in general copies you, what can you do as an artist? Is this my work? Is it being copied, or is it just a trained network generating in the trained style? So people are started to talk about these problems, and I think that the next 5 years we'll see a lot of improvements and strides in these to answer these questions. There's still shortcomings despite all of these very significant breakthroughs, such as humans can learn from a few examples. You just need to show me the image of a weird animal once, and I can detect it. I don't need hundreds of images to train my model to recognize that image, but this is not the case for AI systems. So that concludes my talk. Hope it was useful, and thank you for inviting me.
Thank you for your presentation. Dear participant, do you have any question about these articles? Okay, no question. Thank you again, dear Berna Yanıkoğlu.
I'm going to
for the
correct this
valuable
time.
information
Oh, yeah,
you
thank
have
you. So it's,
provided.
yeah,
I
so
wish
it's
you
been,
continued success in your career. Thank you for joining our invitation.
okay,
I
thank you.
hope you will get better soon. Take care of yourself.
Okay, thank you. Bye-bye.
Yes, first special session is over. Dear participants, thank you for your attending. Dear participants, I would like to end the session. I suggest you to attend the next session, which will start shortly at 11 o'clock. See you in the next session. Good morning. Goodbye.
Bye.